Energy is another way of viewing physics, and theoretically, anything you could do with force, you could do with energy, and vice versa. In practice, anything I give you that you can do with energy methods, it's always going to be vastly easier. There are some things that force is really, really the right way to do it, easier, but they're not on the test. Any time when you can use energy, do use energy, and life is simpler. I will also point out, I cannot tell on a multiple choice test which method you used. I will not tell you you have to use this method. So if you learn what the gospel I am laying out for you today, and the rest of the term, then your life on the final can be much easier, because you can, maybe you didn't master all the force and kinematic stuff, you've got another way to do it. Alternately, you can cross-check your answers a second way, because many of your answers, not all, because energy gives you another way to look at it. What we're working on, no, not potential energy, I pulled that off from today. What we are looking at today, kinetic work and energy conservation are the big three topics today. But as I said, it's two equations and one idea, and you can use this to solve so many problems so easily. I just said this, energy is another way to view physics. Okay, point two. Conservation, I need to announce, I need to define this word. To an ordinary person in English, conservation means you better use it carefully because there's a limited supply and it'll run out, right? Conserve paper, because if you cut down all the trees, it's going to be a long time before there's paper again. In physics, it means exactly sort of the opposite. You never run out of energy. There is no such thing as breaking energy conservation. Now, that's not to say that physicists don't say, don't waste petroleum resources. The energy stored in petroleum deposits, that form of energy will, of course, run out. Energy has lots of forms, and if we put energy ultimately into heat energy, heating up the planet from exhaust, blah, 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 that petroleum energy will no longer be in such a convenient form as able to be transformed to gasoline. It is much, much harder to go from CO2 emissions back to gasoline. I can't think of how it could possibly be done than to go from gasoline to moving cars and stuff. So I am not claiming that physicists believe that you should not be careful with your energy usage and the different forms are important. But I am saying that the total amount, if you add up all of the different objects carrying, all of the different forms they carry, that number never changes. And we're going to use that principle again and again and again today and throughout the rest of the term. I should be precise and say the energy of an isolated system is conserved. If you are thinking of a kid on a sled, we'll do this example in a second, and somebody else shoves the kid on the sled, I'm not saying that the energy of the kid on the sled doesn't change. An external object gave it some energy. So the deeper idea is an isolated system has total energy, no changey. If the energy is changing, it is changing because of an external transfer in, and the amount of change is exactly equal to the amount of transfer in. I will always give you enough to find out either the transfer in, or that'll be the question, or it'll obviously be zero. So say an isolated system. So, total energy is conserved. It might change form, might change objects, but it doesn't change. The total doesn't change. Analogy. Suppose energy is your bank account. Work, the transfer of energy by forces, is a paycheck or whatever, a payment to something external. I claim that your bank account balance really shouldn't change unless either you get paid or you pay someone, right? Moreover, as we'll talk about later, there are multiple forms of energy. We're going to focus on just one real form today. That's like having more than one kind of bank account, a checking and a savings. You can transfer from checking to savings, savings to checking, right? Right? But if you add together both of those forms, if you take your total worth, say checkings plus savings, that amount should not change unless somebody gives you some money or you give somebody some money, unless there's positive or negative work done. Is that a straightforward idea? Great. That's energy conservation in a nutshell. We're just going to apply that to physics. That's all you need to know. Energy has many forms, as I said. We're going to start with one form. I'm going to talk about that one form of energy all day. Okay, so kinetic energy is energy of motion. Remember, kinesis, or however you say it in Greek, means motion. So kinetic energy is motion energy. There is a formula. Memorize it real fast. It's not that hard. Half mv squared. Bam. M is mass, duh. V is speed, actually. Velocity has a plus or a minus, an up or a down, a left or a right. Who cares about that? If you're moving, you're moving. That's all that energy cares about. There is no up-down energy versus left-right energy. There is no positive energy. Well, kinetic energy is never negative. You dying there? Okay. Units. The unit of any kind of energy, work, any transfer in, whatever, is dollars. Your bank account is joules, just like your checks, your paychecks are in dollars and your bank account are in dollars. Work and energy of all forms are joules, and this is the same. This is always the same. A joule is a compound unit. Joule isn't fundamental. You can build up a joule, kilograms, meters squared per second squared. Who's done dimensional analysis in chemistry or whatever? If you know dimensional analysis, Merry Christmas. If you don't know about dimensional analysis, I will not ask you this specific question. This is a tool that you can apply if you know what it means. Okay, again, I want to emphasize there is no such thing as up, down, left, right, in, out, north, out, northwest, southeast energy. Kinetic energy is a scalar. It is a pure number. Good. So that's the one form of energy we're going to talk about today. Now let's talk about work. Work is defined with the equation. This is also not that hard. Oh my God, a trig function. I'll simplify it for you in a second. Force times displacement times the cosine of the angle between force and displacement. Much more on the angle in a second. Okay. Properly, I should emphasize that if you're multiplying force as a number times displacement as a number, those would both better be constant. If force changes as you move, that's not true. With the force of a spring equation, what happened is the object moves, the force gets bigger and bigger, right? So if and when we do springs, depending on how things are going, I may or may not add spring equation. Work would be, we will find it is the area under a force displacement graph. We'll use that to solve for stuff later. This is just how you find the total multiplying two things that aren't constant. Integral. I will not give you a problem explicitly using this. This is a tool we're going to use later in class to find something. Now, let's talk about that theta. I presume you know what force is. Hopefully, God, I hope. I presume you know what displacements are. Let's talk about angle. Cosine of theta, you do not need to use a calculator to find cosine of angle. I am never going to give you a cosine that you cannot do as follows. Let's think about what it means for work to give you or take away some energy, right? You can have positive or negative or zero work. Work is how a force gives something energy. If work is positive, energy is going up, yeah? Right? If work is negative, that force is sucking energy out of something. As an example, if I'm walking along and somebody gives me a shove in the back, which direction is the force? Which direction is the displacement? In the same direction. If force is pushing you, helping your motion, pushing you in the direction you're going. Displacement and force are in the same direction. That is a positive work. The angle between left and left is 1, 0. Cosine of 0 is 1, positive 1. Cosine of 0 is positive 1, so we get to use positive force times distance. If you don't know the cosine function, here we go. You can learn, think, meditate upon this. If force and displacement are working in the same direction, force times distance. Moved. Bam. Right? Suppose I jump up. What direction is force? As I am going upward, what direction is my displacement? What's the angle that I have to rotate to go from down to up? Okay, now let's think about the work done by gravity. Is gravity speeding me up or slowing me down as I rise? So is gravity helping or hindering? It's subtracting some energy out of me. Yeah, right? Okay, if gravity is subtracting energy, if a force is adding negative work, doing negative work subtracts off of your energy, sucking energy out of you rather than putting energy into you, cos of 180 is -1. Work is negative. So, think about this. If the force is helping you, positive Fx, delta x. If the force is opposing your motion, negative F delta x. Yeah, delta x. What if the force is at right angles? We talked about forces at right angles briefly. If I'm moving horizontally, gravity forces down, as the rumor goes. Is gravity helping me move? No. No. Gravity is doing nada for my motion. It is not pushing me along. It is not opposing my motion. So if cosine, what is the angle between my displacement and the force of gravity? Cos of 90 is 0. Now, you future doctors, remind me, how many of you are MCAT, going to take MCAT? Fair number, right? Really? Only if you, come on, hold them higher. Is it really only? Oh, okay. How about more? OAT might as well. I don't think DAT cares about this. You will very likely be given problems, in which case the angle is 30 or 45 or 60 or whatever. Then Merry Christmas, there's a formula. You'll see that in your studies, in your review, in your MCAT prep. For everybody else's case, for this semester, for our classes level that I'm teaching at, you can say if the force is helping, positive force times distance. If help is hindering, negative force times distance. If force is at right angles, neither helping nor hindering, 0 work done. And all this goes back to cos of 0 is 1, cos of 180 is -1, cos of 90 is 0. Think about it whichever way makes sense to you. If you know trig, if you don't know trig, pick one. Do you guys know the word anti-parallel? Have I used that before? I have, right? Here's parallel. Here is anti-parallel. Okay? Vectors have direction. They're not just lines. They're directed lines. They can be opposite or same. Parallel, anti-parallel, yeah. All this is what I just said, of course. Also, these slides are posted. You don't need to write every word. I encourage you to summarize. Summarize. If force helpy, positive. If force hurty, negative. If force right angles, nada. How do you feel about this? So far, so easy squeezy? Well, don't worry. When we get to apply it, it'll turn out to be actually really kind of just as easy as before. Let's apply it. I give you one bunny, pushes another bunny, and he, or pulls, I say, pulls on a rope, pulls horizontally so there's no angle. Well, I ask you to find the work the big bunny does as well as the pulling bunny does on the sister and sled. I give you the distance. I had a question in the 3 o'clock class. Does the 20 kilos include Max? No. 20 kilos is the sled and Maya, and the sled and Maya alone. The total mass would be 35 kilos. Okay. Again, find the work done when Max pulls with that force over that distance. This is Google question A. This one you could talk to each other. Talk to each other. Oh. How much a force gives an energy? How much energy a force causes? It's hard for him to pull something. Just like. It's hard for him to pull something. This reflects how much food he needs to have eaten to do it. So the unit for something that adds to energy has to be the same as the unit for energy. If work adds to energy, the unit must be the same as for energy.
Wait, so where do you get the more? Remember W equals W equals the fourth and the child. W equals 4 times whatever.
All right, here we go. Yeah, always give me the answer. Here we go. I asked you to find the work. By the way, hey, I should point out, any force can deliver work. Any force can do work. In general, every force that applies to an object does work on that object. That work might be zero. For instance, like I described earlier, weight force does absolutely no work to me. There is a weight force on me. It is not doing work. I'm not moving up or down right now. So, which force did I ask to find? Force that Max is exerting on the sled? So use the force that Max exerts on the sled. How much force is that? 12 newtons. What's the other part of work formula? Is F times displacement, delta x. How far does the sled go? 25 meters. Okay, so 12 times 25, now finally, is Max helping, hindering, or nothinging? Helping. Max is moving the sled. He's the one pulling her along. Yeah? So if Max is exerting a force of 12 newtons and causing a displacement of 25 meters, what if there's friction? Is there friction in this problem? Does it matter? Not at all. You got a force, you got a displacement, bam, you've got the work done. 300 joules is the correct answer. Oh, joules, as I said before, work, energy, all those things, joules. Yeah.
If there would be friction, wouldn't the friction cancel out the applied force?
Let's talk about that in a second. If there is friction, what is let's say there's enough friction to move at constant velocity. What's the total force on Maya? She's moving at constant velocity. What's the total force? Google Farm B. Somebody moving at constant velocity has this much total force. How could you find the total force if she is moving constant velocity? Top, 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 top. Again, the question is, if Maya is moving at constant velocity, what is her net force? Don't break the laws. If you're moving at constant velocity, what must your acceleration be?
Yeah.
Okay. Most people are not breaking the law. The law, Newton's law, says that net force equals mass times acceleration. If you are not accelerating, constant velocity, if you are not accelerating, there could be no net force on you. So if there's 12 newtons of pull force and no net force, how much is friction? How much friction is there? 12 newtons. If the total is 0 and you're pulling with 12, friction must be providing 12 backwards, right? Tell me this, riddle me this, Batman. What's the work done by friction? There's a displacement. You're moving at constant velocity. You're moving. This exact problem. I'm just saying that you're moving at constant velocity. There's enough friction. Huh? Almost, but not quite the exact same. It's negative 300. Friction is this away if she's moving that away. Right? Okay. So what's the total work done on Maya? 0. Which says that Max is delivering energy to her. Friction is sucking energy out of her. The total change in her total energy is 0. Does she speed up? Does she slow down? No. If net force is 0, it has to be.
Maya with that sled would not be moving, right?
Constant velocity does not mean 0 velocity. If you're moving with constant velocity, here's me moving with constant velocity. Am I moving? Yeah, you betcha. If the total work done on you is 0, that says that you are not changing your energy, not that there is 0 energy. If there is no work on you, that doesn't mean that you don't have energy. It means that your energy is not being added to or subtracted from. Does that make sense for y'all? Did y'all hear his question? He asked if there's no total work done, does that mean you're not moving, that you have no kinetic energy? If you're moving at constant velocity, you've got motion energy. Work isn't equal to energy. Work is how a force is, or forces, how a or multiple forces are adding or subtracting energy from you. My bank account balance never changes. I never get paid more than I spend. Does that mean I have $0 exactly? No, my bank account balance happens to be $23.05. Yeah, well, hey, I'm a professor, yeah, 10 years. I got 23 bucks. My paycheck balances my expenditures. That doesn't mean that I have $0. It means it never changes. Yeah.
There won't be.
That's what acceleration and velocity are related. Yes. If velocity is constant, A is 0.
There is, there won't be any force.
Net force. If you are pulling with 12 newtons, that's how we deduced that friction must be -12. Yeah.
Unmerited.
Good, good. Reach physics enlightenment. Other questions? I love him. I love him so much. I hope you all are listening to his questions and my answers, by the way. Listen to each other. Learn from each other. Yeah. Just like the crazy farmer. Learn from each other. Okay, so follow up. Let's suppose there's no friction. How fast is she moving? Suppose there's no friction and they start from rest. How fast is she moving at those 25 meters? Well, so there's no friction to suck energy out. He delivers 300 joules of energy. How fast is she moving? No, you don't need time. You do not need time. You start with 0 energy. You deliver 300 joules of energy. What form do you get? What is the only form we know about right now? It's kinetic energy, right? Huh? 300 what? Joules. Joules aren't speed. 300 joules of kinetic energy now. Find the speed. That's the question. Google question C. Follow C. Yeah, Google question C. Find Maya's speed, assuming no friction, and that she starts from rest. Correct answer. C. C, my friends. C. Letter C. That is the letter after B, not D. Hey, sanity check here. You should always think about the numbers given. I will say that bunnies aren't actually, 15 kilos. Whoa, baby, that'd be a big bunny. Nor do they sit on sleds and pull their sisters. But these force values and kids aren't crazy. So if you get that something is moving at the speed of an airplane, you did it wrong. I'll say that 1 meter per second is 2 miles an hour-ish. So please sanity check yourself. Is it possibly reasonable that you're moving at 0.01 meters per second? No, not really. Is it possibly reasonable that you're moving at 250 meters per second? No, that's how fast a jet flies.
Be great. Yeah, instead of swearing, yeah. Just get.
I got five. Okay, wait. Is that reasonable? 5.5? Oh, for-
1 mile an hour is 1 meter per second is about 2 miles an hour. It's 11 meters per 11 miles an hour. That's fast. That's fast. Not impossible.
This week. Oh, hold on. No, no, hold on.
I think I put this one else.
Huh? I would like you to reflect briefly. I would like you to reflect briefly on what you would need to do in order to find this with previous methods. I give you force, I give you mass, what do you get? Oh, come on. Acceleration. If you've got acceleration and distance, how do you get final velocity? Google form D. Let's see who remembers how to get velocity out of acceleration and distance. What equation from unit 1 gives us final velocity in terms of distance? Google D. What's the relationship between velocity, acceleration, and distance? Again, you should be relating the variables V, A, and D. If time appears in your equation, that's not what I'm talking about. Now that's what I'm talking about. Again, for the people online who did not hear, I want you to understand how much harder this is with force kinematics land. I want you to state the equation that relates if you've got acceleration and distance displacement. What's velocity? What equation connects V, A, and D? Oh, people remember. Some people. D. You know what? Screw it. I'm just going to start taking off the points, and that will ease my aching heart. What is the kinematic equation relating velocity, acceleration, and distance? How do you relate V, A, and D? I'm pleasantly surprised. Good job. V final squared equals V initial squared plus 2A delta X. Hey, hold on a second. Hold on a second. V final squared equals V initial squared plus 2A delta X. Humor me for a second. Multiply this by half mass. Each term multiplied by half mass. What's half mass final velocity squared? Final kinetic. What's half mass initial velocity squared? Initial kinetic. 1/2 mass times 2, well, let's see, 1/2 times 2 cancels, yeah? What's mass times acceleration? Which force? Be precise. Net force. Oh my sweet baby Jesus. Total work changes kinetic energy from initial to final. Bam, there you go. If you do not remember the kinematics form, all you need to know is the idea that work changes energy, and there you go. Okay. Or just learn the kinematics equations. Okay, so I do have more. Not much, but a bit. Kinetic energy is motion energy. Work energy represents interaction energy. At a fundamental level, that's all there is. That's all there is at a fundamental foundational level. Everything else comes from this, from one of these. The other forms of energy are, well, motion energy is bam, done. The other forms of energy are all ultimately hidden work energies. Stored work. We're going to reflect not external transfers in, but changes from one account to another inside your system. Potential and internal energies, or what we call these, we'll discuss these next time. Well, we'll get, what, 2 more equations? 1 or 2 more equations. Bam, there we go. We're done. No, we're not done, don't go. Well, unless you have to. Okay. For today, for the rest of today, and probably for the beginning of Monday, we'll still deal with only kinetic energies, which is to say that work done by one force at a time is only going to go into kinetic form. I want to bang on this for a second. Work changes energy, so what if there's no external forces? There's nothing to change your energy. In the absence of external work to change your energy, I use capital E for total energy. That, I hope, is not a big surprise. E, energy. So if there's no external work, your total energy doesn't change. And for our simple systems, for a point particle system, the internal energies, potential energies don't exist. So the only form of energy is kinetic that we're dealing with. For everything that we're doing, if there are no external forces, your total kinetic energy can't change. Your total kinetic energy can't change. What does kinetic energy come from? Total kinetic energy comes from what? What terms appear in kinetic energy? What's kinetic energy equation? Half mass times speed squared. Okay. Does your mass change in general? If you eat or throw up, that's external systems. If you're isolated, your mass is not changing. So what does this say? If there are no external forces doing work on you, what does that say about your speed? Newton's first law, baby. In the absence of external forces, your speed is constant. Cool. Newton's laws and the principles of energy are tied together. They both describe the same thing. Make sense? It's all connected. There are actually ways to get from energy directly to Newton's laws and vice versa, but that's beyond the scope of this course. Okay. Here is a god-awful system that you cannot possibly do. I would really struggle to do this with half an hour's work. Here's a very difficult system that you cannot do without energy methods. Right? Ew. You don't have steady motion in a straight line. You don't have forces pushing you straight down. I'm going to give you a couple of bigly hints here, and we'll make this more sophisticated later. There are a couple of different forces going on a roller coaster rider. Again, we're ignoring drag. Arizona's too conservative, no drag. So just normal and weight force. Normal force here does no work. Normal is perpendicular to the track. Normal is always perpendicular to the surface, right? Remember, it's the meaning of normal. If you're moving along the track, and you better darn well be moving along the track, you're moving perpendicular to the force. Does normal do work? If your force is perpendicular to your motion, does that do work? No, no. That's what I said earlier, right? If you're going this way and normal's that way, that does no work. If you're going this way and normal's that way, it does no work. No matter what angle you're going at as you go down this loop-de-loop hill valley thing, normal does no work. So what does work? What's the only other force? Gravity is the one and only thing. Weight is the only thing that does work as you go up and down. Now, weight goes down. Displacement is all sorts of crazy directions. Right? Yeah? I will give you the bigly hint that displacement cos theta always picks out height. That is to say, gravity's work doesn't care about sideways. Gravity only cares about up down. If you move down 25 meters, if you hit the ground, or went at an angle and went 25 meters down, gravity is still only doing the work from force times your vertical distance. So in all of this, I don't give you any horizontal information. You don't need horizontal information. Just look at the vertical distance moved. Okay? Ready, set, go. Oh, this point B here is very clearly marked, and that's not what I'm asking about. Do not find the speed at V. Find the speed here at 3 meters height. 3 meters height. 3. Okay, and again, this is Google form what? What are we at? This is the same problem as before. It's just forces weight instead of forces 12. Are we measuring V in joules now, my friends? Am I asking for energies?
No, it starts with breast. We have vision loss. We have vision loss. I just have vision. One more time for the people that did not hear this. If you want this question, it is the question on the board. You can read on the board. If you can't see the question on the board, it says, how fast are you moving when you arrive at the 3-meter height. As I wrote here, it says find velocity here. Find velocity when you are at this height. Oh my God, so many correct answers. I'm dying of happiness. It's like things make sense. Mostly. Hey, 10 seconds. Give me your best. Okay, that's good enough. Bless you. Okay, the solution to this problem is exactly the method, the attack to this problem is exactly what we did before. I'm just changing the force. Instead of 12, it's weight. Hey, what's the weight formula? mg. You don't know mass. Uh-oh. Uh-oh. You don't know mass. Not even Catholics know this mass. Hey. However, if I write down the equation, half mass times speed squared, what is that? What does that tell you? The kinetic energy, like we did before, equals, where does that kinetic energy come from? Work. Work done. What is the initial kinetic? Zero. You start from rest. Yeah. Okay. So this kinetic energy comes from work done by weight. And the work formula is force times distance, not zero, force times distance, force times, I'm going to emphasize that it is the up-down direction, change in height. If I go down, I call that y. And looky, mass cancels. Egads. Okay, now I ask you this. If I start 25 meters high and I end 3 meters high, is my work positive or negative? Is gravity doing positive or negative work? Is gravity helping me move down or stopping me from moving down? Shh, think with me, think with me. Is gravity helping me or stopping me? Helping me. Gravity likes things to move down. So is that work positive or negative? Hey, think of it this way. Which direction is the force of gravity? Which direction is the displacement? Cosine of 0 is 1. So, that's expensive. So the correct answer is positive mg distance moved in the vertical direction. What I would plug in here to find, well, let me do this one step at a time. 2 times 10 times from 25 to 3, I'm going to plug in positive 22 meters because the full number is positive. Equivalently, if you wanted to, you could plug in negative mg for the force direction, negative 22 for the height. And then I get rid of the square by squirting it. Final answer, 20-ish meters per second. 21. Whatever. Turn to your neighbor and discuss.
So I can, no, instead of.
Give me a question. Ask me a question. Shh. Listen to each other's questions. Ask me a question. He's not here, so y'all have to pick up the slack. Yeah. What? What about it? Force. The force I'm talking about is the force of weight. Weight is mg. Good. Yes. Yes, if you are not going up or down, gravity does no work. I mean, if you think about it, right? Gravity doesn't help me move sideways. Gravity points this way. That's not helping. Other questions? Okay. Now, yeah. Don't use this formula. Use these techniques. There are two formulas. Half mv squared, force times distance, positive, negative, zero, depending on whether it makes sense. And you can do anything with any of these. Don't use results from one problem in another problem's context. You'll die. Yeah. How do we get the change in y? Well, if I start 25 meters high and I end 3 meters high, how much height how far down did I go?
Like where we at?
Why we added? What do you mean? Where? What's the formula for work? Force times distance, baby. Learn it, love it. It's only two symbols. You can do it. Work is force times distance. The distance that I gave the hint down, gravity doesn't care about left, right? The distance down is 22 meters. The force is mg. We're talking about the work done by weight. Yeah. Mm-hmm. Yeah, what's K? Kinetic energy, where's that come from? What is making this energy? What?
I just asking for.
So no, kinetic energy is defined as 1/2 mv squared. K equals half mv squared is the defining equation for kinetic energy. But I ask you this, where does that kinetic energy come from? What is causing that? Yeah, which force? So how does a force give energy? What is the idea that connects force and energy? What is the name of the quantity that we give that gets from force land to energy land? Work. That's the defining idea for work. Work, again, shh, listen, think. Work is how a force gives or subtracts energy from something. Yeah? That's why we used equals work. Kinetic energy given equals, well, the hint that I gave is the force that delivers this is weight force. So I found the weight work. Okay. So I'm going to give you a quiz answer. Class is over unless you want a quiz answer, in which case go quietly and quickly, please. But you may go. You have everything necessary to do it, but I'm going to tell you the answer real fast in a minute. Go on, go on. Those of you who do not want to listen, get out of here. Or who have other places to be, or have something else doing. You have all the skills necessary to do it. I'm just going to guide the people who struggle with algebra through. If you're good at algebra, go. But go fast, go on. Okay, the rest of you want the quiz answer? Great. Well, I'm not just going to tell you like what you plug in. I'm going to reason about it real fast. I ask you, here I'm building up to the answer. I'll give you the pieces real fast. Here, no, this looks too intimidating. This looks too intimidating. La pregunta es, the question I ask is how big are we going? How high are we going? How high are we? How high are you compared to your initial height when you are moving at half your initial speed? The physics of it, the scenario of it is I roll down one ramp, up another ramp. You can't do this with forces. You don't know enough. I didn't teach you about forces on ramps. You roll down one ramp, up another ramp. I'm saying your speed at the bottom, we're going to use this in a second. Speed at the bottom is Vmax, max speed. And I'm asking you, how high are you? How high, man? When your speed is half of your maximum speed. You roll down, you roll up. You don't necessarily go up all the way when you're moving half as fast. Actually, you can't be all the way up when you're moving half as fast because you're still moving, you're not at your max height, right? Okay. So, how high are we? Oh, so high, man. I'm going to use the principle that we go down a distance, we go down some distance from our initial height, I'm saying is HI. No, I'm not giving you numbers, by the way. This is symbolic. You guys have used letters. We can use letters to represent things. We don't have to do everything with numbers. So. How far do we go down? What is the distance we go down? Well, that's what I want. I'm asking for where you end up. Although I would say if you start HI above the ground and you end HF above the ground, what is your displacement? It's not HF. HI minus HF, right? So I would say the work done by gravity in this whole process is the weight of the object times how far it moves. The work done is exactly what we've been doing, force times distance. Force mg, distance involves what we look for. Okay, and what is that work? What form is that going into? We're going to start at rest. That goes into the only form you know about, kinetic energy. That work gets delivered into the final kinetic energy form, which is half mass. Wait, what is the velocity? Half of, oh, we don't know Vmax yet, but we've got a symbol for it and we can find it. So I'm just going to write the symbol. Please be careful. Vmax over 2 squared is a different number than Vmax squared over 2. If you have a fraction and you square it, upstairs and downstairs, it's squared, right? Okay, so I've got this formula. I'm almost done, except I don't know Vmax, yeah. So I say that weight force is down, displacement is down. I want a positive number, yeah? HI is bigger than HF. HI minus HF is the magnitude of the displacement. I'm looking at magnitude of the weight, magnitude of the displacement. Okay, so I'm given HI. I'm asking in terms of HI. M cancels, obviously, you see here. I just need to find Vmax and I'm done. So how do you find Vmax? Well, ignore the fact you're going back up and just look at how much work does weight do going down. How much work does weight do when I go down all the initial height? Well, mg times hi, right? Positive. Work is positive when I go all the way down. Equals what? Not height. Hi equals height. What's mghi? The work of what? The work of the weight force. Exactly. When and where? What did you say? What are we finding? The work done by the weight force when we get all the way to the bottom. Why the bottom? Because I don't know Vmax. I want to know Vmax, so I use the total work done when I get to Vmax. Okay, so if I go down hi meters, I pick up mghi energy. What form does that go into? Kinetic energy. So I write down the kinetic energy formula. 1/2 mass times what? How fast am I going then? Turn to your neighbor, discuss for 2 seconds. How fast am I going at the bottom of the track? How fast am I going? That's what I'm looking for. That's why I'm doing this. That's the source of this. Is it Vmax or is it half Vmax? It was half up here. Why is it whole down there? Say it again. It's not HF over here. You use all of Vmax because this is two different things. This is at final question conditions, still moving, some height up. This is at the bottom. When I'm at the bottom, that's as fast as I'm getting. I'm getting all of the work done, all of the possible work done. Gravity has moved me a full distance down. Yeah, right? So I get all of the max speed. The challenge is to find when are we at this speed, so I'd use that displacement goes with that kinetic energy. Turn to your neighbor and they'll explain each other what's in here. This is the same stuff that we did in the previous problems, just with letters. That's all the only difference here. Discuss 2 seconds. No acceleration. Screw acceleration. Ask me a question before we move on. I'd like you actually to understand this. Please. It's the same formula as I'm ever doing. What is causing a kinetic energy? Gravity is doing work. Work done by gravity is the kinetic energy at that time. Work done by gravity is kinetic energy at that time. There's only one equation. I'm just applying it at different places. When I'm at my final place, I don't know where I am. That's the goal. So I say, I make up a letter, HF, to represent it. I'm going to solve for HF later. And say the work done to get to that height, total work done that the gravity does when I'm at that height, and the speed at that height, kinetic energy at that height comes from the speed at that height. That's what I gave, that's the question. And then I don't know Vmax. I refer to Vmax,
but I want my final answer in terms of h's. What the h? So I need to do something about Vmax. Where is it Vmax? It's at the bottom. So I apply the same principles. When I'm at the bottom, I've got this much work done. And I've got this much speed energy, kinetic energy. Yeah. That's the logical process. It's only one idea. How much energy have you got? How much work has gravity done? What's the only form we've talked about yet? Okay, now let's practice the principles of algebra. Let's deal with the first equation and the second equation separately. First equation, m cancels. So I get g times hi minus hf equals 1, well, hold on, let's say Vmax over 2 squared is what? What's Vmax over 2 squared? Go farm! What is half of Vmax squared? Google F. Google form F. Google form F. What is Vmax over 2 squared? What happens when you multiply Vmax over 2 by itself? And I'm glad I asked this, because we need to practice. Okay, I will encourage you to think about the meaning of squaring. Squaring means multiplying a number by itself. Imagine Vmax is 1, okay? What's 1 over 2 squared? What's 1/2 times a half? Half times a half of a half is a quarter. Is it 1? No, that's 2 times a half is 1. Half times a half squared, is a quarter. So when you have a fraction squared, the upstairs gets squared and the downstairs gets squared. This is half Vmax squared over 4. Alright. What's half times Vmax squared over 4? Can I simplify that? Google form, what is half times something over 4? Google G. Simplify the right-hand side for me. Google form, Google form, Google form G. How do I multiply two fractions? Okay, so here's how I multiply fractions. I multiply tops and I multiply bottoms. If you think about this, multiplying by 1/2 is the same thing of taking half of a number. If this is my number and I want it to be half as big, what do I have to do to the downstairs to make it half as big? Double? Double the downstairs, yeah. Okay, so Vmax squared over 8 equals this mess here. Now I'm going to take this equation and simplify it. Well, there's only really one thing I do to there. GH initial equals half Vmax squared. Well, this is easy peasy lemon squeezy. I want Vmax squared. This equation, I could solve Vmax squared. I don't even need to take the square root. 2g high. Okay with my algebra? Multiply both sides by 2. Take this and shove it. Take this and shove it for v squared. You don't have to take a square root. You're just going to square it again. That's silly. Vmax squared equals 2ghi. Plug her in. Next line. G high minus huff equals 2ghi over 8. And a g cancels g. What's 2 over 8? Last time I checked, it was 1/4. How do I simplify the right-hand side then? I multiply by 4. 4 high minus huff equals high. How do I multiply 4 by something that is subtracted? 4 high minus 4 huff equals high. I'm being silly here. If I want huff, I bring him over to this side and get rid of him. So I add 4 high to both sides. I subtract high, add 4 HF to both sides, subtract HI from both sides, and I'm left with, if I've got 4 of something and I subtract 1 of it, I'm left with 3 HIs. Bam, Merry Christmas. There's the answer for the rest. Hopefully the literally half of the class that left will be able to get this too. Please let me encourage you, don't let them cheat. I mean, seriously. If and you have any questions, my office hours are awfully lonely. I'll be up here for several minutes. But we done. I love you all. Bye.